Hello guys, and in this video we will explore FAT file systems. Hoping after watching this video, the FAT file systems will be open book for you, and you will understand the structure of those file systems. So you will understand how to perform forensic analysis on FAT32, FAT16 file systems. You will understand the structural data, the layout of the file system, the metadata for the files and folders on different external media formatted in FAT32 and FAT16. And also, at the end of the video, I will show you a couple of examples of automated processing of FAT32 file system using the Autopsy software. Okay, let's get started. In FAT file systems, FAT stands for File Allocation Table. And this means that file allocations, so the clusters that allocated to some file, is tracked by the file system using those file allocation tables. And we see different variants of FAT file systems in a while. First of all, quite legacy file systems like FAT12 and FAT16. Probably you will not see FAT12 anymore, but FAT16 may exist on some smaller capacity USB memory sticks up to 1 or 2 gigabytes. Most frequently, you will see a FAT32 file system, which is used on external storage media devices like USB memory sticks and SD cards. And the newest file system in this FAT file system family is extended FAT, which stands, or exFAT, which a bit more advanced in comparison with FAT32. It has a larger addressable space than FAT32, which means that you can format larger volumes with this file system. It has more timestamps and metadata for the files, and also has a space pre-allocation functionality, meaning that you can pre-allocate some space on a drive for storing the bigger, larger files. In this video, we will cover FAT16 and FAT32, and I will create an additional video explaining the exFAT contents. If you compare FAT16 and FAT32 file systems, in FAT16 only 2 bytes are used for cluster addressing, which makes the maximum cluster number equal to 65,535, and the cluster numbering starts from 2. Also on those drives exist 2 areas, the system area and data area. The system area usually located in the beginning of the drive, and it's not expandable. This area contains structural information of the file system, like volume boot record and 2 FAT tables. But it also contains a root directory and all entries that belongs to root directory. In opposite to that, FAT32 file systems already have 3 bytes or 28-bit are used for cluster addressing. That makes possible to create more clusters and to format larger volumes with this file system. So the maximum cluster number exceeds 16 million, and also cluster numbering starts from 2. This file system also has a system area and data area. System area not expandable and contains a volume boot record and 2 FAT tables, but root directory is shifted to the data area, which actually makes this root directory extensible, which means that you actually can create as many files as you need in this directory until, of course, you have enough space on your drive. Let's have a more graphical example of this comparison.
So if we look at this picture, we have here two file systems, FAT16 and FAT32 schematic representation. And as you see, both volumes starts with this system area, which stores structural information starting from the volume boot record and following several reserved sectors and two file allocation tables, one main table and one backup table. After that, in FAT16 file system, the root directory is preserved. So this system area is not expandable, so it cannot grow. That's why root directory is has a fixed size and can accommodate only a fixed number of files inside it. In comparison to that, in FAT32, the root directory is shifted down into data area, and data area is the area where the files and folders store its information. And in this situation, the root directory can grow in size until you have space in a data area of the volume. In both file systems, the clustering starts from 2, and if the cluster size is not well aligned with the volume size, then there will be a volume slack at the end of formatted volume. That would mean that there will be several sectors that are not used by the file system but still exist on this partition. So let's zoom in on the volume boot record. And the volume boot record is usually located in the very first logical sector of the formatted volume. And from all the information that we see here, the most important is the byte offsets 4 to 8, which stores the utility name that is used to format this drive. In our case, it's MS-DOS 5.0 because we formatted this drive in Windows. If it would be Linux, for example, there would be a utility name that, for example, could be mkfs.fat utility that you can use in Linux to format drives with FAT32 file system. And also at the offset 14 here, we have a number that shows us how many physical sectors are used to form one cluster. And so basically using this number, if we want to know what is the cluster size in this particular file system, we have to multiply it by 512 and get, in this case, 4096 bytes or 4K cluster size on this disk. And a couple of bytes after that are used to show the number of the sectors between the volume boot record and the first file allocation table. So this is offset at the first file allocation table that we see here. And also important offsets are, for example, the offsets 29 to 32, here marked in green. And those offsets tells us how many sectors are between this particular volume boot record, so beginning of this volume, and the disk physical sector 0, beginning of the disk. In our case, it's 0, means this volume boot record also is the very first sector of our USB memory stick. And in addition to this, at the offset 42, we have a flag 29, which signals us that this is an extended boot signature. And also signals us that this flag will be followed by the uh, volume label, which is by default no name, and the file system type, which is FAT32. And this all are ASCII encoding, so you can see it right away from the screen. And no name is not the label that the user inserts when it formats when the user formats the drive. So remember, for our drive, I used label removable. So this removable label will go to root directory. So this label is usually stays hidden from the user, and in many cases it stays on its default value, which is no name. Okay, let's have an example in FTK Imager. Okay, let's have an example. This is a freshly formatted external USB device, external USB memory stick that is formatted with FAT32 file system and opened in Access Data FTK Imager. So all the instances that we see here are created during the formatting process. I haven't added anything here. And if we are on the level of the physical drive in evidence tree, so we see actually the very first sector of the disk, and you already can recognize that this is a volume boot record of the disk, and we can recognize it by looking at the name of the utility that was used to create this volume, in this case MS-DOS 5.0. And also we see here a label, no name, and a file system type, which is FAT32. It's your default values for formatted drives on a Windows. And if we expand an evidence tree here, so we can go to this removable FAT32 layer, and that is actual representation of FTK Imager of all the structural information, structural metadata for this specific drive. And here, all this information represented for our convenience as different instances. So, for example, volume boot record represented separately, reserved sectors between the volume boot record end and the start of the first file location table is also presented separately. We can just select this instance and navigate that. And physical, as you see, we are from physical sector 1 to physical sector 1049. And at the physical sector 1050, the file allocation table starts. And if we look at those sizes here, those sizes are actually the sizes in kilobytes for those instances. For the root directory, it will be 4K. And by the way, by this size, you right away can identify the cluster size as well. So the root directory will occupy at least one cluster on freshly formatted volume, but then it will grow in size when you start to add instances, files and folders in this directory. And also the sizes for allocation tables and reserve sectors are in kilobytes. But for the VBR, it is actually size in sectors, which is only 512 bytes. In addition to the structural information on a drive, during the formatting, the root directory is created. And in Windows specifically, under the root directory, the system volume information will be created by default, which holds a couple of files, for example, indexer volume GUID, file that stores GUID number for this specific device. And the root directory starts usually in cluster 2, as you see here, the cluster number, In it, we'll have entries for files and full subfolders. So let's zoom in root directory contents and we'll understand the metadata that it contains. For FAT32 directory entry demonstration, I have created an image from removable drive, and using a Python script, I created some directories on this drive with the name subfolder 0 to subfolder 9, and I put some text files inside those directories. And the text files all have the name document, and the contents of file will show also the index of this file. So basically, using this example, you can follow along and investigate directory entries together with me. This image is available on Google Drive, and you can download it using a link below the video. So first of all, we need to understand the contents of the directory entries because it's very important for the forensic investigations to understand it. First of all, because the directory entries store all the metadata that relate to the files and folders on a drive. Directory entries store timestamps, file name, physical location, information about the file, file attributes, and file size information. So all information that is needed to describe a certain file or folder. And when we're looking at directory entries, we are usually operate with 32 byte entries. And for each and every file, there will be two entries on directory entry. The first entry will be the base entry or base record, which is 32 bytes long and which starts with a file name that is converted to DOS 8.3 format. And also, for each and every file, there will be at least 32 bytes used to store a long file name entry, which is abbreviated as LFN. LFN store file name in Unicode and occupies at least 32 bytes, but depending on the file name length, it can occupy more than one entry. And the first 32 bytes in root directory store the volume name that the user has specified during the disk formatting. So if we look at our disk in cluster 2, we see the contents of the root directory, and basically it starts with 32 byte entries storing the volume label. In our case, it's removable. So the first 32 bytes are only used for this volume label. And after that, you see, I have marked with different colors. So we have here in this root directory a system volume information folder. We have a folder subfolder 0. And we have a bunch of documents. I just created the screenshot from first 3 entries from the root directory. And for each and every file or folder, there will be a long file name entry. For example, for the system volume information, it will be 64 bytes long. So two 32 byte long entries are used to store the name of this directory in Unicode. As you see, it's readable here, like you start from the second entry, system, volume, and go to this first entry, information. So the reading of those file names and folder names are usually from bottom up. And for the same file, the base entry is created. And the base entry here also 32 bytes in length. And the base entry starts with this DOS 8.3 converted file name. So as you see, this is shortened and uppercased file name with a tilde and index for this directory. And after that, this file name, there will be a metadata related to this specific folder. And on the next slide, we will look at this metadata in detail. So after this base entry, there is a long file name entry for the subfolder folder on a disk, and the base entry with the same structure as the previous one and with the same length of 32 bytes. And the same entry exists for each and every document in this folder. So document 5, for example, that follows the subfolder 1 also has a long file name entry here, and you can read it, document 5, and it has a DOS 8.3 converted name document tilde 1 txt in a base entry with all related metadata inside. So first of all, let's dig into this base entry and try to interpret all the values that we see here. Let's have a closer look to the base entry for the document file 5 txt file. And if we look at it, we see that the first 11 bytes in base entry are allocated to store the file name, which is uppercase document tilde 1 txt. And last 3 bytes are used to store the extension of the file in uppercase. First 6 usually store the first 6 letters from the file name, and tilde 1 actually, as we have many files in this directory with the similar names, this tilde and index will be used to distinguish between different entries for different files. After the file name, 1 byte is allocated to store the attributes, and you need to convert this value into binary to see the attributes for a specific file. In our case, if we convert that, we see that it is can be interpreted as archive or normal file. So if you have some other value here, so you need to convert it to binary to see where are the ones and accordingly interpret that. So there can be several ones for one file or folder inside a file attribute. So basically you can combine several options from this list. The 1 byte here is reserved, and the next byte will show the value of the creation time, milliseconds. So when the file is created, the milliseconds value of the creation time is stored here. You need to convert that to decimal to get the millisecond value here. After that, 2 bytes are used to store the file creation time. And this is creation time in DOS format, which has quite weird conversion mechanism. But FTK Imager and pretty much all the forensic software is capable to convert this value into the normal timestamp. And this is the local time, so it represents the system time at the moment of the creation of the file. And the next 2 bytes is the date of the creation. So again, 2 bytes in DOS format. After that, 2 bytes are used to store the date of the last access to the file. And after that, 2 bytes here, coupled with 2 bytes here. And those 4 bytes are storing the cluster address from where this file content is starting. So basically, if I go to this cluster, then I will look at the very beginning of the file content there. And those two are higher bits, and actually only one of those is in use, and those are lower bits, and both uh, bytes are used here. So, for example, for this specific file, if I want to know in which cluster this file starts, I uh, read from right to left, starting from higher bits, so 0, 0, 0, 0, 0, 0, 10, and that will give me a 10th cluster. So this file content starts in the cluster number 10. If I jump there, so I should see the text of this document 5 text. And here in the middle, 2 bytes are used to store file modification timestamps, time of the modification of the file data, and the date of the modification of the file data in DOS format. And last 4 bytes are used to store the file size in bytes. And if I look at this closely, the maximum value you can have here is all F's in hex, which makes a bit more than 4 gigabytes of maximum file size. So if you want to store a file that is more than this value, so larger than 4 gigs, so the file system will not allow you to do so. And that is a limitation of FAT32 file system. Okay, let's get back to our disk and try to interpret some values from there. So I now opened the FAT32 example 01 disk image in FTK Imager, and let's explore the contents of the root directory here. So as we saw previously, the first 32 bytes are allocated to store the volume label for the drive, and after that the entries for the files and folders are created. Let's look closely at the base entry for the system volume information. As you see here, it starts with the DOS 8.3 converted folder name, which is system-1. So in total, 11 bytes are allocated to store this converted folder name for the folder. As the folder doesn't have any extension, so the last 3 bytes are filled with the values of 20. And for the documents, for example, the files, those values are representing the extension in the file name. So our base record for the system folder has a flag of 16. And if we convert this flag in binary, so we will get the value of 0001010, and if we look at those attributes closely, the first one here will mean that this is a directory, and this one would mean that this is a system directory, and this one here would mean that is hidden. So we are looking now at the hidden system directory, which is true for the system volume information. And for the document text, the same value would be 20, which is a normal file or archive. Then let's get back to the base entry for the system volume information. So here we have a creation time for this specific directory. And if we look at how this interpreted in our FTK measure, so we definitely should ignore here the DOS date, which is incorrect, but only the DOS time is correctly interpreted here. So the time of the creation is local time for this system. And the date of the creation here is opposite. We are looking at the converted DOS date, which is 9/11/2021, and we ignore the DOS time. So just this is incorrect value here. And after that, the last access date also converted. Then the content modification time, which is 12/19/14 p.m. Corresponds to the creation time for this system volume information. I haven't put any file in this directory, so it matches the creation time and the creation date, of course. And if we want to know from which cluster this system volume information directory starts, we need to look at those higher bit for the cluster address and those lower bit of the cluster address. And starting reading from here, 00, 03, which makes 3 in decimal, and that would mean that this directory starts in a cluster 3 on the disk. And for the directories, the entries for the directory size are always zeros, so the entry doesn't have any values here. However, we know that physically this specific directory at least have two files. That would mean at least 64 bytes that needed to be allocated for the directory contents. So usually at least one cluster is allocated to store the contents of the directory. So let's go to the file system level and quickly navigate to the cluster 3 on this volume to look at the contents of this system volume information directory. So as we see here, the system volume information directory has two files. We previously briefly spoke about it. So index volume file and VP settings file. And for the subdirectories, and in our case, all the subfolders and the system volume information will be a subdirectory from the root directory. As we see here, the subdirectories also contains the entries of the files that are stored inside those directories, the same long file name for the file, and base entry for the file. Let's look at the first two entries or first 64 bytes of the system volume information directory. And actually what we see here is two entries. First starting with the 2E, and this is converted to dot in ASCII. And the second entry here starts with the 2E, 2E, or double dot. So it's dot to dot notations. And what does it mean? Basically, the first entry here is used to track the location of this current directory, so system volume information. So the values that we have here, starting from here, actually correspond to normal file or folder values. So we have here timestamps for the creation, date for the access, the contents modification timestamps for this current directory, and also we have here an address where this current directory starts. So if we convert those 2 bytes and also look at the higher bytes here, which are zeroed, then we will get the cluster size of this directory. system volume information directory. And if we look at the next entry here, this is an entry for the mother directory of its system volume information directory. Again, we have here timestamps, different timestamps of this root directory in this case, and also we have an address of the root directory. And in our case, as we have here zeros, then it would mean for the file system that this system volume information is located in very root of the directory tree. But let's have an example of subfolder 8. Here we have again 64 bytes in the beginning, and the directory itself, the subfolder 8 directory, is located in cluster 14. We converted these values into 14, and you see here we are in a cluster 14. The directory in which this subfolder 8 resides is in a cluster 13, and if we go to the cluster 13, then we obviously will see the contents of this subfolder 7. So we can go to the file system level and go to the cluster 13, and let's see what we have here. And indeed we have the directory names that is located in this directory, which is subfolder 8. So it would mean that we are now in the subfolder 7. So that is how the FAT file system's tracking the directories. So information about the this mother directory is residing inside the subfolder or subdirectory, and this process repeats until we reach the root directory. So you can imagine, for example, if we lose some information here, we lose this folder, then this daisy chain will be broken here. So we looked what information is created when the files and folders are created in FAT32, but let's look what happens if we delete folders and files in FAT32 file system. So I'm now in my removable drive, and let's try to delete some contents of it. So for example, I will delete this document 4 here. I just push delete and have the notification that this file is deleted. I go to subfolder 0. Let's delete a couple of files here, document 8 and 9, for example, from here. I will go, for example, to subfolder 3, subfolder 2, and let's first of all, I will go to the subfolder, the very last one, subfolder 9, and here in a 9 subfolder I have two files with very long file names, and I will delete the first one here, push delete button here, and I will go, for example, in subfolder 5, and I will delete everything that resides beneath the subfolder 6. So I will delete the subfolder 6, and I will delete everything inside the subfolder 6. So I now have created a forensic image from the removable drive with those all those deleted files, and I opened that in Access Data FTK Imager. The same image is available for you for investigation from the Google Drive, and link is below the video. So if I expand it and go to my root directory here, remember from this directory I deleted the document 4, but what I see here in the file list, this file name is still present, but only the this icon orientation for the file has changed in FTK, and it has now a red cross symbolizing that we are looking at deleted file entry. But let's investigate the root directory entries. Here I will go to the hex window and try to locate the base entry for this document 4. And here I have a base entry with the tilde 4 in a DOS name. But if you remember that base entry is always below the long file name entry, so actually this document tilde 4 belongs to document 3. So you shouldn't think that this is a part of the file name. This is actually an index that file system adds to the document name. But our document 4 that I have deleted, the long file name for this document, long file name entry for this document actually resides here. And as we see, we deleted the files, but the directory entry is still persists on the drive. So it's not overwritten, it's not gone anywhere. And also the base entry here, it's also not gone anywhere. That would mean that we still have all those metadata, bytes, timestamps, and information about the file content location in clusters. So for example, for this specific file, the file content is located in cluster 24. So we have all this information still there, available for us. But what actually happened when user deleted the file is that the only very first byte of this entry was changed, and it was changed to the value E5 in hex. And this indicates the file system that this is a deleted entry, and you should hide it from the user, and you are able, so file system is able now to overwrite the contents of those clusters. But as we hasn't created any new files here, actually the old data wasn't overwritten but by anything else, and that would mean after deletion we still are able to recover the file content here. So recovery would mean that we still have a metadata for this file, and based on this metadata we can get the contents of the file. And as you see, all the timestamps and the file name and the content is recoverable. So for example, if I hit the click the right mouse button and choose here export files, so I can export this file actually to my desktop, and it will be available for me, and also I can get all the metadata for this file, which is great for the forensics because we are able restore files after they are deleted. So let's expand a bit this contents, and remember we deleted the subfolder 6 as well, and also in subfolder let's see the other subfolders here. We deleted document 8 and 9 in subfolder 1, and as you see, at the same reason, the contents is still available to us because in these entries, also the very first byte for the entry only changed to E5, but all the rest is still present. But yes, we have deleted the subfolder 6, and this is in the content of subfolder 5. So if we go to this subfolder 5, and try to see the entry for the subfolder 6. Here it is. So this first byte is changed to E5. But again, all beneath the subfolder file is actually deleted. So user think that those files are gone, but they are not. They are still recoverable until the very last one. And also, let's look for the some files in subdirectory 9, which has this very long file name, and what happens after deletion. Here we have this first file with a very long file name. That would mean that this file has an LFN entry of this size. And as you see in this LFN entry, so at the beginning of each 32-byte entry, also the first byte is changed to E5. So and in the base entry as well. So this is the what happening when somebody is deleting the file, and that gives a lot of opportunity for the recovery of the files. But if we, for example, create a new files here, so what do you think if we will be able still to recover those previously deleted files or not? Let's have an example of that as well. So let's have some more fun with this removable FAT32 drive. What I did is, in addition to those folders that already was in a drive and some deleted files that we covered just a minute ago, I created a number of folders here with a script. And in some of the folders, I also uploaded some files. So basically, for example, in this newly created subfolder 11, I have now 10 additional files created with the contents love. So I tried to fill this folder with love. And the other folders are basically empty. So I have created an image of this, and this image is also available from the link below the video. And the image name is FAT32 example 01 deleted and overwritten. So let's look at deleted the file contents that we had on the drive. So in the subfolder 0, we had this document4 file. And before we created some new files here, the content was recoverable here. And if I now click on it, then we see that FTK Imager is not able to show us the contents. And why is that? Let's look closely to the root directory entry of this file. So it is at the end of the root directory entry. You see here the long file name entry for the file, which starts with the E5 for the deleted file, and a base entry. And using this base entry, we can see in which cluster the file was. And let's navigate to this cluster now and see what happened with this cluster. So I will go to the file system level, and I will go to the cluster 24. If I will jump there, so we see that, okay, this cluster now is occupied with some subdirectory entry. And if we read the long file name here, we see that this is subdirectory or subfolder 16. If we go down a bit, so I'm just hitting page down on my keyboard and go one cluster down from here, we see that actually The next cluster, cluster 25, is occupied with the subfolder 17 now. So basically those new subfolders were created at the same clusters where the document for content was. That would mean that the content of document 4 is actually overwritten entirely, and there is no magic bullet to recover this content anymore. Let's look at the others deleted files. So for example here document 9. So document 9 is still available here, so meaning that nor metadata and the content both are not overwritten with the new files, so you can really export this file from here and get all the metadata for the file. And what happened with this document 8? So document 8 is not recoverable, at least automatically by this FTK imager. Let's look at the subfolder 0 entries and try to, in a hex windows, try to locate the document 8 entry here. Now I see it's at the bottom. So I have this long file name entry and I have a base entry, and what I'm interested in which cluster this document was. And it was in the cluster 41. Let's navigate to this cluster and see what is there. So I will go to the file system level first and go to sector cluster and choose the sector cluster 41. Jump there, and what I see here is this cluster is overwritten with a subfolder 19. If I go scroll down a bit to the next cluster, then let's see what we have there. So the next cluster here, cluster 42, is also overwritten with the subfolder 20. But if I, for example, navigate to cluster 43, what I will see there, 43 is also have a subfolder entry, and actually this is subfolder 20, which is actually empty. There is nothing in there. That's why we only have like the header entries for this subfolder. And let's try to go to cluster 44, the next cluster after that. And what we see here actually some content of the file, and you see that this is document 8 content. So what it means that the newly created directories has overwritten the very beginning of this document 8 content, but there is still remainings of this document. So this document 8 is actually partially recoverable. So you can recover some text from this document, but not the entire document. So that's what happened with this one. Let's go to the other deleted stuff here. So subfolder 6, for example. So we see that subfolder 6 is also not recoverable. Let's see in which cluster this subfolder 6 located, and if I interpret this value correctly, it should be in cluster 12. Okay, let's go to the cluster 12 and see what's there. Go to sector cluster 12, and now it has a contents of the subfolder 11, which has this another subfolder of 12. So basically this is overwritten with this stuff, if I'm correct. So meaning that all this information is also gone. Let's get some comparison with this initial drive with only deleted files. What we can find still from. So what I have here is actually two images open in FTK Imager. The image with the overwritten files and only with deleted files. And basically what you can do, how can you practice? You actually can search for both images simultaneously. So for example, you can go to subfolder 8 and see that here is document 50, which is overwritten. And let's see, the document 50 actually was in a cluster 619, and if we, for example, go to the this overwritten disk to the clusters 619. So if we see this data there or no, not. Now it's gone and overwritten. So basically you can have some more fun with those two images, trying to manually carve out the partially overwritten files if it's possible. But the last thing what I want to show you is the automatic recovery process with the autopsy software. So we will examine this FAT32 example with overwritten files in autopsy. So I'm starting my autopsy software. I'm now using 4.19 version, and I will try to process the this image with overwritten files in autopsy. So first of all, I will create a new case here, and let's say FAT32. Yes, this should have an access. FAT32 overwritten, and I will store everything in the space directory, and I hit next. Oh, sorry, I need to put it somewhere, so I will put it on my desktop, for example, and I hit next. And here I can fill the case number and my details, but I will not do that for this demonstration. And I will hit finish. Then the autopsy will create a case for me, and then I will be able to add an image to the case. So first of all, I will leave this first value at default because we have this removable drive, so we will not specify any host name for this. And from this list of data source types, I will select a disk image because I already have a disk image, and I will browse to this disk image on my disk. And here we have this example with overwritten files. I will open that. And here, as we are investigating FAT file system, so if I select ignore orphan files, that would mean that it will not recover subfolders, deleted subfolders if this subfolder daisy chain is broken. So definitely for the FAT disks, I will not enable this feature, so it should be empty. And then this is my time zone. I will leave it default. And the sector size, as I know that this is a healthy file system, so I do not have to specify that. The autopsy will figure out itself that the sector size is 4K for this disk. and I hit next. And basically, for the sake of this demonstration, we will not use ingests that doesn't help us. But however, if you are looking at some drive that is not familiar to you, you never know what's on it, so you can specify the more ingests for yourself. So first of all, what I will leave on is recent activity. I will leave this hash lookup, will disable this hash lookup. File type identification, certainly I need that. Extension mismatch detector, also I need that. I will not use the embedded file extractor because I have only like text files there. Picture analyzer, not this time, not the keyword search, no email parser, no encryption detection. And now interesting file identifier for that. Now central repository, I definitely leave Photorec Carver. This is the utility that actually recovers this deleted information. I don't have any virtual machines there, and nothing to deal with data source integrity, Android, and drone analyzer. So basically, I will leave only Photorec Carver for this specific demonstration. And then I hit next, and I will wait for the results to pop. So the autopsy has finished the processing, and here I have the results. Let's expand the results. I'm sorry for the small text here, but I cannot make it bigger at the moment. So basically here we have our drive represented in different views. This is our disk, basically pretty much in the same manner as we saw it in FTK Imager, with some differences. So in sorting of root directory contents. So what it was able to find, let's see, nothing in orphan files, so no directories that were unreachable from the root, deleted directories. Let's see the subfolders. There are only actual subfolders persist, so the subfolders that are not overwritten is possible to get from here. Subfolder 6 again, so it's possible to see, but it's not possible to get the content because content is not there. But if we look at the deleted files, for example, and here we have 4 instances discovered from the deleted instances. Let's look at them. So subfolder 6 with no content. The autopsy only capable to provide me metadata entry for this subfolder 6. So this is remember, from the directory entry of subfolder 5. We get all this metadata. And here we just have those automatically processed results visible. Let's look at those 3 documents. Remember that document 9 was recoverable, so we still have the contents, and it's also available here. Document 4 was not recoverable at all, so it was overwritten. And what autopsy shows me actually here, show me the contents of the cluster that it gets from the directory entry. And show me that, okay, here is a contents of this subfolder 15, basically. So if somebody is not familiar with and do not understand this directory entries, then probably he may think that, okay, this is an actual content of document 4, which is not. But you already have this knowledge in place, you quickly distinguish that, okay, this is not belonging to this initial document 4. And for the document 8 is the same situation. So we have here the same information that was created by this new folder creation is connected to this document 8, which is not correct, of course. So that is why it's important to really understand how the file systems are behaving and how they are structured. So this was a very long video, and thank you very much for watching this. In the next video, I will try to cover the FAT file system in the same manner as I covered the FAT32 file system in this video. Thank you very much.